Right now, as you watch this, Earth is doing something almost no other place in the universe appears to be doing. It's alive. Not just habitable, not just warm enough for liquid water, actually biologically, chemically, irreversibly alive. Microbes in the soil, forests pulling carbon from the air, oceans full of organisms that have been running the same chemical reactions for billions of years. From where you're sitting, this feels ordinary. It is not ordinary. It may be one of the rarest things in the universe. Here's the question that's going to drive everything we talk about today. Astronomers estimate that our galaxy alone contains at least 100 billion planets. 100 billion. That number doesn't register the way it should. Think about it this way. If you counted one planet per second without stopping, it would take you over 3,000 years to count them all. And that's just the Milky Way. The observable universe contains somewhere around 2 trillion galaxies. So the total number of planets out there is essentially beyond any frame of reference we have. It's a number so large it stops meaning anything. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. And yet, as far as we can tell, we are alone. We have found no confirmed signal of life anywhere else. No second biosphere, no alien microbe, no distant civilization. Nothing. With all those planets, all that time, all that space, the universe appears to be almost completely silent. That tension between the staggering number of worlds and the apparent absence of life on any of them is exactly what we're going to explore. But here's what most people don't fully appreciate. When astronomers look at the actual planets we've discovered, the vast majority of them look nothing like Earth. We've found gas giants orbiting closer to their stars than Mercury orbits ours. We've found rocky worlds where the surface temperature melts iron. We've found planets with no atmospheres at all, just bare rock rotating under a star's radiation. We've found worlds so tidally distorted by their star's gravity that they're stretched into shapes you wouldn't recognize as planets. Of the roughly 6,300 confirmed exoplanets as of 2026, only a small handful sit in the range where liquid water might exist on a rocky surface. Only a few dozen candidates out of thousands examined, and even most of those probably aren't alive. That word, dead, is the one we're going to be living with for the rest of this video. Dead worlds. Planets that either never had the conditions for life to start, or had them once and lost them. Mars lost its magnetic field and its atmosphere. Venus went through a greenhouse spiral it could never reverse. Other worlds got blasted by radiation from unstable stars. Some never got a chance because they formed too close, too small, or around the wrong kind of star. There are many ways for a world to die, and we're going to go through all of them. We'll start with what makes a world dead in the first place, because the definition matters more than you might think. Then we'll go through the mechanisms, the magnetic field collapses, the atmospheric stripping, the runaway heating, the stellar flares, the tidal forces that literally bake planets from the inside out. We'll look at the most common types of planets we've found and explain why most of them are almost certainly lifeless. And then, at the end, we're going to try to put an actual number on it. How many dead worlds are there in the universe? The answer is going to be a number so large that even writing it down feels almost pointless. The universe is not a place full of worlds teeming with life and waiting to be found. The picture that emerges from everything we know about planets, stars, atmospheres, and chemistry is of a vast, cold, largely silent graveyard. Billions of rocky worlds stripped of their air. Billions more scorched beyond recognition. Trillions of rogue planets drifting through the dark with no star at all. The the rare exceptions, worlds like Earth, alive and running, appear to be genuinely extraordinary against that backdrop. And by the time we're done, you're going to have a sense of just how crowded that graveyard might be. The word dead sounds simple enough, but when astronomers use it, they're usually describing something more specific than just a world with no life on it. A world with no life isn't automatically a dead world. The moon has no life on it. Neither does Mercury. Neither, as far as we know, does every single confirmed exoplanet in our catalog. But astronomers don't call all of those dead. They call them sterile or barren or uninhabitable. Dead means something different. Dead implies that something was lost, or that something necessary was never there to begin with, or that a process failed somewhere along the way that could have gone differently. The distinction matters because it changes what we're actually counting when we try to estimate how many dead worlds exist. If dead just means no life, the number is almost every planet we've ever found. That's not a very useful definition. It doesn't tell us anything about how close those worlds came to being something else. And the closeness is exactly what's interesting. Scientists generally think about dead worlds in three categories. The first is worlds that experienced catastrophic collapse, worlds that had something going for them, maybe liquid water, maybe the right chemistry, maybe a stable climate, and then lost it. Mars is the clearest example we have. It had rivers, it had oceans. It had an atmosphere thick enough to hold liquid water on its surface for hundreds of millions of years. Then a series of failures compounded on each other, and it became what it is today. Cold, airless, frozen. That's a world that died, not a world that was always dead. The second category is worlds in the right location that never got the chemistry started. These are planets sitting in what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a surface, but where conditions never allowed the right molecules to assemble in the right way. Maybe the atmosphere was always the wrong composition. Maybe the surface was too geologically stable and never cycled the elements that prebiotic chemistry requires. Maybe the water was there, but nothing happened in it. These worlds aren't dead in the way Mars is dead. They never had anything to lose. But they're dead in the sense that they represent failed opportunities. Worlds where the conditions were met in some narrow technical sense and life still didn't emerge. The third category is worlds that were dead from the moment they formed. Hot Jupiters, gas giants orbiting so close to their stars that a year lasts only a few days, were never going to harbor life. Rocky planets locked in tight orbits around violent young stars, blasted by radiation before they even finished forming, never had a chance. These worlds didn't die. They were born dead. The difference sounds philosophical, but it's actually practical. When scientists try to figure out how many dead worlds the universe contains, they need to know which of those three bins each planet falls into, because each bin has different implications for how common life might be elsewhere. There's also an important distinction between sterile and dead that's worth holding on to. A sterile world is one where life isn't present. A dead world, in the deeper sense, is one where life couldn't be present, where the conditions that life requires have been permanently removed or never existed. Antarctica is sterile in large parts of it. It isn't dead. Microbial life survives in extremely cold, dry environments on Earth that would look uninhabitable at first glance. Scientists use the word dead carefully because a world that looks lifeless from orbit might not be lifeless everywhere, at every depth, in every niche. Habitability isn't a binary, it's a spectrum. A world can be partially habitable, perhaps only in certain regions, only at certain depths, only during certain periods of its history. Scientists increasingly think about planetary habitability the way they think about a dimmer switch rather than a light switch. Earth is at full brightness. Mars right now is close to off. But it may not always have been. And that matters for how we think about what dead really means. Think about what that implies for the estimate we're building toward. If there are billions of rocky planets sitting in habitable zones around distant stars, and we're asking how many of them are dead, the answer depends entirely on which definition we use and which category each of those worlds falls into. The worlds that were always going to be dead from formation represent one kind of loss. The worlds that were in the right zone but never sparked represent another. And then there's the third category, the hardest one to think about. Worlds that had liquid water, worlds that had stable atmospheres, worlds that were on the edge of something and then fell off. Worlds where the conditions were met long enough that the question of whether life began there is genuinely open, and then the conditions ended. It's that third category, the worlds that almost made it, that tells us the most about how rare places like Earth might actually be. Mars is the dead world we know best, and that's exactly what makes it so useful. Every other dead world we've found is a point of light, something we measure from a distance, something we infer. Mars we've touched. We've landed rovers on it, driven across its surface, drilled into its soil, and sent back photographs of its canyon walls and dried riverbeds. We know what it looks like up close, and what it looks like up close is the aftermath of a catastrophe that played out over billions of years. 4 billion years ago, Mars was not the frozen red desert we see today. It had river channels wide enough to swallow entire cities. It had lowland regions that most scientists now believe held a shallow ocean covering a significant portion of the northern hemisphere. Its atmosphere was thicker, denser, warm enough to keep water liquid at the surface. The atmospheric pressure was high enough to matter. If you'd stood on Mars roughly 4 billion years ago, it wouldn't have looked anything like it does now. It would have looked in some ways like a place worth visiting, possibly a place where something could live. Scientists haven't found proof of ancient Martian life, but the conditions in that early window were not obviously hostile to it. The chemistry was there, the water was there, the warmth was there. Whatever was going to happen on Mars, it had a reasonable starting position. Then it fell apart. Not slowly, not gradually. It fell apart in a cascade, each collapse triggering the next. The first thing to go was the core. Mars is smaller than Earth. It has roughly half the diameter and about 1/10 the mass. Smaller bodies lose internal heat faster because they have more surface area relative to their volume. Earth is still geologically active today, still generating heat from its interior, still churning the liquid iron in its outer core. Mars cooled faster. The internal heat that drives the geodynamo, the process that generates a magnetic field, dissipated more quickly. Around 4.2 billion years ago, Mars's global magnetic field began to fail. This wasn't a minor development. This was the beginning of the end. A magnetic field does one critical thing: it deflects the solar wind. The solar wind is a constant stream of charged particles flowing outward from the sun at hundreds of miles per second. On Earth, the magnetic field wraps around the planet and redirects most of those particles harmlessly around us. On Mars, once the field collapsed, there was nothing left to do. That job. The solar wind hit the upper atmosphere directly. What followed was atmospheric stripping, and it happened on a scale that's difficult to comprehend. NASA's MAVEN spacecraft measured it directly. The solar wind is currently stripping away Martian atmosphere at a rate of about 100 grams per second. That sounds modest. But run that process for billions of years across a period when the young sun was more active and more violent than it is now, and the losses become staggering. Scientists estimate that roughly a third of Mars's original carbon dioxide was lost to solar wind sputtering alone. The atmosphere didn't leak away, it was torn away. As the atmosphere thinned, the surface pressure dropped. And as the pressure dropped, liquid water couldn't survive at the surface. Water that had been sitting in rivers and ocean basins either evaporated into an atmosphere that could no longer hold it, or froze into the ground and the polar ice caps. The surface temperatures, no longer buffered by a meaningful atmosphere, swung to extremes. Today, Mars hits temperatures of around -80 degrees Fahrenheit on average, dropping to -195 degrees Fahrenheit near the poles in winter. The rivers are gone. The ocean is gone. Even most of the atmosphere is gone. What remains is less than 1% as dense as Earth's. Think about where Mars sits. It's in our solar system's habitable zone, not at the edge of it, not barely clinging to the inner boundary. It gets enough sunlight. Its distance from the sun is not what killed it. Mars died in the habitable zone. It had the right address and still couldn't survive. That's the point. Being in the habitable zone is necessary, but it is nowhere near sufficient. What killed Mars was a sequence of failures that locked together. The core cooled. The magnetic field went. The atmosphere was exposed. The solar wind stripped it. The pressure dropped. The water disappeared. Each step made the next one worse. There was no single moment where Mars could have been saved by fixing one thing. Once the core cooled past a critical threshold, everything else followed. The cascade was built into the physics of a small rocky planet orbiting an active young star, and that's what makes Mars so valuable to study. It gives us a template, a world roughly in the right location with water and atmosphere in its early history that couldn't hold on to what it had. We can read the sequence in the rocks, in the crater record, in the magnetic signatures baked into ancient terrain from a time when the field still existed. Mars is legible. We can understand what happened to it because we've been there, because we've analyzed its minerals and mapped its topography and modeled its ancient climate. Most dead worlds in the universe we'll never get closer to than a point of light in a telescope. If Mars shows us one way a world can die, Venus shows us the other. And in some ways, Venus is the more terrifying lesson. Mars is cold. Mars is thin. Mars is quiet. You can look at Mars and understand, at least emotionally, what happened to it. It ran out of warmth and protection and slowly faded. Venus is something else entirely. Venus is a furnace. The surface temperature on Venus is about 880 degrees Fahrenheit. That's 471 degrees Celsius. It's hot enough to melt lead. It's hotter than Mercury, even though Mercury is twice as close to the sun. The atmospheric pressure at the surface of Venus is 92 times what you'd feel standing on Earth. Soviet probes landed there in the 1970s and 1980s. The longest any of them survived was about 2 hours before the heat and pressure destroyed them completely. Not damaged, destroyed. The atmosphere is almost entirely carbon dioxide, dense enough to crush metal, thick enough to trap heat with no way out. And it rains sulfuric acid, not water. Sulfuric acid, falling from clouds that permanently blanket the entire planet. There is no view of the surface from space. There is no break in the clouds. Just a permanent toxic shroud over a world that is completely, irreversibly dead. Here's what makes Venus so unsettling. Venus is not some alien world made from exotic material found nowhere else in the solar system. Venus is almost exactly the same size as Earth. Its diameter is about 95% of Earth's. Its mass is about 82% of Earth's. It formed at roughly the same time from the same disk of gas and dust that produced every other planet. If you lined up Earth and Venus side by side, they'd look like siblings. Same basic composition, same general structure, a rocky inner planet with a hot core, a mantle, a crust. From a distance, you might mistake one for the other, and yet one of them is teeming with life, covered in oceans, wrapped in breathable air. The other is a hellscape where nothing survives. The difference between a living world and a dead one in this case came down to distance and a feedback loop. When the solar system was young, the sun was dimmer, about 30% dimmer than it is today. That matters enormously. Early Venus, under a fainter sun and sitting slightly closer to it than Earth, may have had liquid water on its surface. Some scientists think it had oceans, not as deep as Earth's perhaps, not as long-lasting, but real bodies of water, sitting on a real rocky surface with a real atmosphere above them. Whether life had any chance to emerge in that window is something we don't know. But the conditions weren't obviously impossible. The early solar system was a violent place, but Venus had time. It had warmth. It had water. And then the sun started to brighten. As the sun grew more luminous over millions of years, Venus got warmer. Warmer surface water began to evaporate. Water vapor entered the atmosphere. And here's the critical thing about water vapor. It's a greenhouse gas, a powerful one. More water vapor in the atmosphere meant more heat trapped at the surface. More heat at the surface meant more ocean water evaporating. More evaporation meant even more water vapor. More water vapor meant even more heat. The cycle fed itself. Each step made the next step worse. This is the runaway greenhouse effect, and once it starts, there's no natural mechanism to stop it. The oceans eventually boiled away entirely. The water vapor in the upper atmosphere was broken apart by ultraviolet radiation from the sun. The hydrogen escaped into space. The oxygen combined with surface rocks. The water was gone. All of it. And without water to cycle carbon back into the ground through geological processes, carbon dioxide built up in the atmosphere and just stayed there. The planet crossed a threshold it could never return from. That's what makes this different from ordinary climate change. On Earth, there are feedback mechanisms that moderate temperature over long timescales. Carbon gets absorbed into the ocean. Silicate weathering pulls carbon dioxide out of the air. Plate tectonics buries carbon-rich rock. These cycles act as a thermostat. Venus lost its thermostat when it lost its water. After that, there was nothing to regulate anything. The carbon dioxide just accumulated. The heat just built. The pressure just increased. Over hundreds of millions of years, Venus became what it is today. Think about what that means in practical terms. Venus didn't need to be hit by a massive asteroid. It didn't need a catastrophic volcanic event. It didn't need its core to collapse or its magnetic field to disappear. It just needed to be in a slightly worse position than Earth when the sun started to age, a little closer to the inner edge of the habitable zone, a little more vulnerable to the feedback loop that warming started. That's it. That's the difference. A world that might have had water and a world that has sulfuric acid rain, separated by nothing more than orbital position and a spiral that ran away before anything could stop it. Every star in the galaxy has an inner edge to its habitable zone. Get too close, and the same process that destroyed Venus plays out again. The sun brightens a little, the water evaporates a little, the greenhouse warms a little, and then it's over. Billions of planets in the universe sit closer to their stars than Venus does to ours, and every one of them is a dead world for exactly this reason. Earth has an invisible shield, and most people don't think about it because it's never failed us. It's called the magnetosphere, and it wraps around the entire planet, generated deep underground by processes that have been running continuously for billions of years. Without it, Earth would look very different. Without it, Earth might look like Mars. Here's how it works. At the center of the Earth is a solid iron core. Surrounding that is a layer of liquid iron and nickel roughly 1,400 miles thick. That liquid layer is constantly moving. Heat flowing outward from the inner core drives convection currents through the molten metal, and those currents carry electrical charge. Moving electrical charge generates a magnetic field. The whole system is called the geodynamo, and it produces a magnetic field that extends tens of thousands of miles out into space, far beyond the surface, far beyond the atmosphere. What does that field actually do? Think of the solar wind, the continuous stream of charged particles flowing outward from the sun at hundreds of miles per second. Without something to deflect it, that stream would hit the upper atmosphere directly. It would ionize gas molecules in the thermosphere and strip them away. Over millions of years, over billions of years, that process bleeds a planet dry. The atmosphere thins, the surface pressure drops. Liquid water can no longer remain stable on the surface. The planet dies. Earth's magnetic field deflects most of that solar wind before it reaches the atmosphere. The charged particles follow the field lines and are redirected around the planet rather than into it. Some get funneled toward the poles, where they produce the aurora. Those visible light shows are actually a sign that the shield is working, that energy is being safely redirected rather than absorbed. The shield also blocks a significant portion of cosmic radiation from reaching the surface. Life on the ground is largely unaware of the constant bombardment happening thousands of miles overhead. That invisibility is a measure of how well the system works. But here's the part that matters for dead worlds. The geodynamo doesn't run forever. It runs on heat. Specifically, it runs on the temperature difference between the hot inner core and the cooler outer layers of the planet. As a planet ages, that temperature difference gradually decreases. Heat flows outward. The core cools. And as it cools, the convection in the liquid layer slows. If it slows enough, if the liquid layer begins to solidify, the dynamo stops. The magnetic field collapses. The shield disappears. This is not theoretical. It happened to Mars. About 4.2 billion years ago, Mars had a global magnetic field. We know this because ancient magnetized rocks on the Martian surface still carry the signature of that old field, frozen in place like a record of something long gone. Then the field shut down. Mars is smaller than Earth, roughly half the diameter, about 1/10 the mass. A smaller planet has more surface area relative to its volume, which means it loses heat faster. Mars cooled faster than Earth. Its core solidified. Its dynamo stopped. And when it did, the solar wind had direct access to the Martian atmosphere. The stripping began. Within hundreds of millions of years, Mars lost most of its air. The surface pressure fell to less than 1% of Earth's. Liquid water could no longer exist on the surface. The rivers dried up. The oceans evaporated or froze into the ground. The planet that may have had conditions for life became a frozen, irradiated desert. Earth has stayed protected because it's larger. More mass means more internal heat. More heat means the geodynamo have been running for 4 billion years and counting. Earth also benefits from heat generated by the decay of radioactive elements inside the planet, uranium, thorium, potassium, which adds to the total heat budget and slows the cooling process. But Earth's core is still cooling. Recent studies have shown it may be cooling faster than previously estimated. The field is not static. It shifts, it weakens in places. It has reversed its polarity many times over geological history. Right now, the field is measurably weaker than it was a few centuries ago. That doesn't mean it's about to fail. The timescale is probably millions of years, but the direction of travel is clear. Eventually, the geodynamo will slow. Eventually, the field will weaken to the point where it no longer protects the atmosphere the way it does today. Earth will not be shielded forever. Now scale that up. Across the galaxy, rocky planets come in a wide range of sizes. Many are smaller than Earth. Many formed billions of years ago around stars older than the Sun. A planet half Earth's size, formed 5 billion years ago around an old star, has had 5 billion years to cool and solidify its core. The probability that its geodynamo is still running is low. The probability that it still has a substantial atmosphere is lower still. Billions of rocky planets in the galaxy are likely in exactly this condition. Some of them orbit in their star's habitable zone. The temperature at the surface would theoretically allow liquid water. The distance from the star is right. The star itself is stable. Everything about the location looks promising, but the shield is gone. The atmosphere was stripped away a billion years ago. The surface is bare rock, irradiated, airless, dead. Location isn't enough. You need the chemistry, you need the water, you need the right temperature, and you need something to protect all of it from the star that warms you. The same star that makes liquid water possible is constantly trying to destroy the conditions that allow it. The magnetic field is the thing that mediates that tension. Without it, the star wins. Sit in the right zone, lose your shield too early, and you end up with a dead rock in a good neighborhood. 7 out of every 10 stars in the Milky Way are red dwarfs, which sounds like good news for the search for life until you look at what living next to one actually means. Red dwarfs are small, dim, and cool compared to our sun. They burn through their fuel so slowly that they can survive for trillions of years, vastly longer than the cosmos has existed. In terms of sheer numbers, they dominate the galaxy completely. And because they're so common, their habitable zones are packed with rocky planets. Astronomers have found them repeatedly, consistently, orbiting red dwarfs in the temperature range where liquid water could theoretically exist. On paper, this looks like a universe generous with opportunities for life. In practice, it may be something else entirely. Imagine a world where the sun never moves, not rising, not setting, not arcing across the sky, just fixed, burning in one spot forever. On the opposite side of the planet, permanent night. Cold, dark, and completely still. No dawn coming, no dusk. Just 2 halves of a world, each trapped in its own extreme. Forever. This is tidal locking, and it's not a rare edge case. For planets orbiting red dwarfs in the habitable zone, it's probably the default condition. Here's why it happens. Every planet exerts a gravitational pull on its star, and every star pulls back on the planet. That pull creates a tidal bulge, a slight stretching of the planet toward the star. If the planet is close enough, that bulge gets dragged by the star's gravity until the planet's rotation slows down and eventually stops relative to its orbit. The planet ends up showing one face to the star permanently. The same way the moon always shows us the same side, these planets always show the same face to their sun. The technical term is synchronous rotation. The practical result is a world split in 2. Red dwarf habitable zones are tight. To receive enough warmth from a dim star, a planet has to orbit much closer than Earth orbits the sun. We're talking orbital periods of days, sometimes less than a week. At those distances, the tidal forces are strong, and the timescale for locking a rocky planet into synchronous rotation is short, potentially just a few 100 million years, which is brief by planetary standards. Most rocky planets in red dwarf habitable zones have had billions of years to become locked. The ones that aren't locked yet probably will be soon. So what does a tidally locked world actually look like? The day side is bathed in continuous stellar radiation. No night to cool things down. No seasonal variation to redistribute heat. Just a permanent noon directly beneath the star. Temperatures on the day side can climb high enough to melt rock in extreme cases, and even in milder scenarios, the constant radiation creates conditions hostile to liquid surface water. On the opposite side, the night side sits in perpetual darkness. Temperatures can plunge to hundreds of degrees below zero. Any atmosphere that reaches the night side can freeze out entirely, essentially collapsing onto the surface as ice. Between these two extremes, there's a narrow strip running around the planet's edge, the terminator zone. Perpetual twilight, the region where the star is always just at the horizon. Early models of tidal locking pointed to this terminator zone as potentially the only place where temperatures might fall in a survivable range, a thin band of twilight on an otherwise extreme world. For a long time, the scientific consensus leaned heavily negative on tidally locked planets. The reasoning was straightforward. If the day side is too hot and the night side is too cold, the atmosphere faces a severe problem. Gases heated on the day side would flow toward the night side, but on a cold enough night side, those gases freeze out and stay there. Over time, the atmosphere drains to the cold side and collapses. No atmosphere means no pressure. No pressure means no liquid water. No liquid water means no life as we understand it. A frozen night side and a scorched day side with no atmosphere left to speak of. More recent modeling has complicated that picture. Climate simulations suggest that under the right conditions, atmospheric circulation on a tidally locked planet could actually redistribute enough heat to prevent the night side from completely freezing. A thick enough atmosphere, the right composition, and ocean currents if liquid water exists at all. These factors might allow a tidally locked world to maintain something closer to equilibrium. Some models even suggest that the terminator zone could support stable liquid water. The debate isn't settled. There are researchers who think tidally locked planets are far more viable than early models suggested, and there are researchers who think the early pessimism was closer to correct. But here's the thing. That debate is happening in isolation. It's asking whether tidal locking alone kills a planet. And the answer to that specific question might actually be no. Some tidally locked planets might distribute heat well enough to avoid atmospheric collapse. Atmospheric dynamics are complex, and we're still learning how they work at these scales. The problem is that tidal locking doesn't arrive alone. A planet tidally locked in a red dwarf habitable zone is also a planet orbiting extremely close to a star that produces violent flares. It's a planet that has been bombarded with high-energy UV radiation since the day it formed. It's a planet whose rocky interior may have cooled fast enough to lose its magnetic field early. It's a planet sitting inside a stellar wind that, with no magnetic shield to deflect it, can strip away atmospheric gases molecule by molecule over billions of years. You can build a climate model that keeps the terminator zone habitable. You can assume the right atmospheric composition and the right circulation patterns. But you still have to get the atmosphere there in the first place and keep it there against everything a red dwarf is throwing at it. Strip away the atmosphere, and it doesn't matter how favorable the terminator zone dynamics are. Freeze the night side into a solid sheet of atmospheric ice, and the circulation stops. Bake the day side with a superflare, and the chemistry falls apart. Tidal locking adds one more constraint to a planet that's already dealing with too many of them. Being in the right zone around the right kind of star means very little if one half of your world never sees daylight and the other half never gets a break from it. Not every dead world is quiet. We've spent time looking at worlds frozen in place, locked in permanent day and permanent night. But there's a different kind of dead world out there, one that's not cold and still, not silent, not slowly losing its atmosphere to the dark. This kind of world is violent, geologically violent, covered in volcanoes, resurfaced constantly by lava, venting gas into the sky in quantities that would be unimaginable by any terrestrial standard. These worlds are dead, and they are furious about it. The mechanism responsible is called tidal heating. Here's how it works. When a planet orbits close to a massive body, gravity pulls on it. But if the orbit isn't perfectly circular, the gravitational pull changes slightly as the planet swings closer and then farther away. The planet gets squeezed and relaxed, over and over again, with every single orbit. That mechanical stress converts directly into heat inside the planet's interior. The effect is the same as bending a metal rod back and forth. Do it enough times and the metal gets warm. For a planet, do it for billions of years and the interior stays molten. We have a perfect example of this in our own solar system. Io is one of Jupiter's moons, and it is the most volcanically active body we have ever found. Not on Earth's level, not on Venus's level, orders of magnitude beyond anything else in the solar system. Io has hundreds of active volcanoes. Its surface is covered in sulfur and silicate lava. Some of its volcanic plumes shoot material hundreds of miles into space. None of this is powered by radioactive decay or residual heat from formation. All of it comes from Jupiter's gravity pulling and squeezing Io as it orbits. With the gravitational influence of the other Galilean moons, Europa and Ganymede, keeping Io's orbit slightly elliptical, preventing it from settling into a circular path that would reduce the heating. Without that orbital eccentricity, the squeezing stops. With it, Io effectively has an internal furnace that never goes out. Now take that process and scale it to exoplanets. Planets in the habitable zones of red dwarfs orbit extremely close to their stars. We've already established that. What we haven't fully addressed yet is what happens when those planets also have neighbors. Red dwarf systems tend to be compact, multiple planets packed into orbits that in our solar system would all fit inside the distance from the Sun to Mercury. When you have several planets in that kind of tight configuration, gravitational interactions between them are constant. Those interactions can force orbital eccentricities onto planets that might otherwise settle into circular paths. And orbital eccentricity in a close orbit around a massive star means tidal heating. Scientists have a name for the extreme outcome. They call them tidal Venuses. A planet that sits in the habitable zone close enough to its star to potentially have liquid water, but subjected to such intense gravitational squeezing that the interior stays perpetually molten. The volcanic activity that results isn't comparable to Earth's plate tectonics, which are relatively gentle and actually help regulate climate over long timescales. This is something far more extreme. Continuous volcanic eruptions releasing sulfur dioxide, carbon dioxide, hydrogen sulfide, and other gases in quantities that rapidly overwhelm any atmospheric chemistry that might otherwise be building towards something interesting. The atmosphere on a tidal Venus doesn't get stripped away the way it does on a magnetically unprotected planet near an active red dwarf. It stays, it thickens. It fills with volcanic gases that make it incompatible with any biochemistry we understand. The surface gets remade constantly. Any minerals or chemical gradients that might support prebiotic chemistry get buried under fresh lava before the process can go anywhere. A world like this might look, from a distance, like it has all the right ingredients, right zone, right size, right temperature range in theory. But the inside is working against everything. The number of planets that may fall into this category is difficult to estimate precisely, but the conditions that produce tidal Venuses are not rare. Compact multi-planet systems are common around red dwarfs. Orbital resonances in tight systems are a natural outcome of planetary formation and migration. The same dynamics that keep Io perpetually erupting are almost certainly operating on billions of exoplanets scattered across the galaxy. Some estimates suggest a significant fraction of potentially habitable zone planets around low-mass stars may experience tidal heating intense enough to render them geologically catastrophic in exactly this way. These worlds are not cold and dark. They are not stripped bare and silent. They glow. Their surfaces pulse with lava. Their atmospheres churn with volcanic chemistry. They are, in their own way, spectacular. And they are completely, utterly hostile to life. Dead does not mean still. Dead does not mean quiet. A world can be geologically violent in every possible way and still be completely, absolutely lifeless. Stars don't stay the same, and that's a problem for any planet hoping to remain alive across billions of years. When we talk about the habitable zone around a star, we tend to describe it like a fixed address, a region in space where liquid water can exist on a rocky surface. Not too hot, not too cold. But that picture is misleading in one critical way. The zone isn't fixed. It moves. As a star ages, it burns through its hydrogen fuel and gradually brightens. The sun today is about 30% more luminous than it was when the solar system formed 4.6 billion years ago. That might not sound like much, but over billions of years, that steady brightening pushes the habitable zone steadily outward, and any planet sitting near its inner edge eventually gets left on the wrong side of the line. The inner edge of the habitable zone is the boundary you don't want to cross. Inside that boundary, a planet cannot maintain liquid water on its surface indefinitely. The star is too close, the radiation too intense. Any surface water begins to evaporate into the atmosphere, and water vapor is a powerful greenhouse gas. More vapor means more warming. More warming means more evaporation. The planet enters a feedback loop it can never escape, and the process accelerates until the oceans are gone and the surface temperature climbs to hundreds or even thousands of degrees. That's the runaway greenhouse effect. Venus is the local example. But Venus is not an isolated case. It's a template. The inner edge isn't a sharp wall, it's a gradient. Planets sitting comfortably inside the habitable zone are safe. Planets sitting well inside the inner edge are already dead. But there's a zone in between, a precarious region near the edge where a planet's fate depends on factors that can shift. A small increase in stellar luminosity, a large volcanic eruption that floods the atmosphere with carbon dioxide, a change in cloud cover that alters how much sunlight the surface reflects. Any one of these things on a planet already close to the edge can be enough to tip the balance. The feedback starts, and once it starts, there's no stopping it. Stars spend billions of years on what astronomers call the main sequence, slowly and steadily brightening as the composition of their cores changes. The sun will be about 10% more luminous in another billion years than it is today. In a billion years, that could be enough to start pushing Earth toward conditions that favor a runaway greenhouse. The habitable zone around the sun will have shifted outward, and Earth's position relative to that zone will have changed. This isn't a distant theoretical concern. It's a scheduled event. The math is already written. For Earth, there's still time. But for planets that formed closer to their stars, or around stars that brightened faster, that deadline already passed. Now scale this across the galaxy. The Milky Way is about 13 billion years old. The oldest stars in it formed billions of years before the Sun did. The habitable zones around those stars have been migrating outward for much longer than ours has. Any rocky planet that formed near the inner edge of one of those zones and started out with liquid water at its surface had a countdown running from the moment it formed. As its star aged and brightened, the habitable zone crept outward. Eventually, the planet found itself inside the inner edge, no longer protected by the geometry of its orbit. The runaway greenhouse ignited. The water left the surface. The planet died. How many worlds have followed this path? Conservatively, the number is enormous. Roughly 20 to 50% of Sun-like stars are thought to have rocky planets in their habitable zones. Many of those planets orbit near the inner edge because that's where rocky planets tend to accumulate in the warmer regions of a protoplanetary disk. Of those inner edge planets, a significant fraction were probably habitable early in their star's life and are not habitable now. Their stars simply got brighter. The zone moved, the worlds didn't. There's no mechanism for a planet to move outward to stay in the sweet spot. It stays where it formed, and the star catches up to it. This dynamic is especially pronounced for planets that formed early in the universe's history, when the first generations of stars were igniting. Those ancient stars have had the longest time to brighten. The planets around them have had the most time to be overtaken by the migrating inner edge. Some of those planets may have harbored liquid water for hundreds of millions of years before the greenhouse took hold. Long enough, in theory, for chemistry to become complex. Long enough for the question of life to be genuinely open. And then the brightening continued, and the question was answered in the harshest possible way. The runaway greenhouse effect is not a rare catastrophe. It's not something that requires unusual circumstances or bad luck. It's a natural consequence of the fact that stars change over time and planets don't move. Every old enough star has pushed its inner habitable zone outward. Every planet that was once near that inner edge has had to reckon with the consequences. The universe is full of worlds that were warm and wet and then weren't. Not because anything violent happened to them, just because enough time passed. Time itself is a mechanism for creating dead worlds, and the universe has had a lot of it. Losing an atmosphere sounds dramatic, but for most planets it happens slowly, quietly, one molecule at a time. There's no explosion, no single event you could point to and say that's when it ended. Just a steady, invisible drain that runs for millions of years until there's nothing left to lose. The first mechanism is called Jean's thermal escape. At the top of any atmosphere, gas molecules are moving at a range of speeds. Most of them are moving too slowly to escape the planet's gravitational pull. But there's always a tail of faster-moving molecules, and the lightest ones, hydrogen, helium, move fastest. When one of those molecules near the top of the atmosphere happens to be moving upward fast enough, there's nothing left to collide with. It just keeps going. It drifts off into space and never comes back. It's a slow leak. Individual molecules, one by one. But over geological timescales, a slow leak is enough to empty a planet's atmosphere of its lightest components entirely. Then there's photoionization. Ultraviolet radiation from a star hits the upper atmosphere and strips electrons from gas molecules, ionizing them. Charged particles behave differently than neutral ones. The solar wind, the constant stream of charged particles flowing outward from a star, can grab those ionized molecules and drag them away from the planet. This process doesn't require the molecules to be moving fast on their own. The star does the work, and it runs continuously every second of every day for billions of years. Solar wind sputtering is related but distinct. Here, the solar wind itself physically collides with atmospheric particles and knocks them loose. Think of it like sandblasting, except the sand is a stream of charged particles and the surface being eroded is the top of a planet's air supply. Scientists estimate that roughly a third of Mars's original carbon dioxide was lost through sputtering alone. Not a third of what's left, a third of what Mars started with. Gone. Molecule by molecule, blasted away by the wind coming off the sun. Impact erosion is the mechanism that tends to get overlooked. Early solar systems were violent environments, the period astronomers call the Late Heavy Bombardment. That peaked roughly 4 billion years ago. Saw the inner planets absorbing impacts from large asteroids and comets at a rate that's almost impossible to picture from the relative calm of today. When a large object strikes a planet at high velocity, the energy release isn't just local. Shock waves propagate through the planet and into the atmosphere. A fraction of the atmosphere directly above the impact site can be accelerated beyond escape velocity. Not just rocks and dust get ejected, air gets ejected. Do that enough times, with enough large impacts. You can strip away a significant fraction of a planet's total atmospheric inventory before any of the slower mechanisms have even really gotten started. None of these processes is necessarily fatal on its own. Earth has been losing atmosphere to Jeans escape and photoionization for 4.5 billion years and still has a substantial one. The difference is that Earth has factors working against the loss, strong gravity that makes escape harder for most molecules, a magnetic field that deflects the solar wind before it can ionize and drag away atmospheric gas, ongoing geological processes that replenish the atmosphere through volcanic outgassing. Take away any one of those protective factors and the math changes. Take away all of them and the outcome becomes inevitable. That's what makes the combination so dangerous. Planets with lower gravity lose atmosphere faster. This was because the escape velocity threshold is lower and more molecules at the tail of the thermal distribution can exceed it. Planets without magnetic fields lose atmosphere faster because there's nothing deflecting the solar wind and photoionization proceeds unchecked. Planets in closer orbits lose atmosphere faster. This was because the stellar radiation is more intense and the solar wind is denser at shorter distances, and planets orbiting more active stars lose atmosphere faster. This was because more flares mean more high-energy radiation arriving at shorter intervals. Each factor multiplies the rate of loss. Stack them together and you don't get a slow drain. You get something that can strip a planet bare within a few 100 million years. Think about what that means for the population of rocky planets in the galaxy. Red dwarfs, which make up the majority of stars, have habitable zones that sit extremely close to the star. Planets there are getting hammered by intense radiation and a dense solar wind. Many of those planets are small, formed from the same material as Mars or smaller. Small planets have lower gravity and cool their interiors faster, which means they lose their magnetic field sooner. So you have planets that are close to an active star, low mass, and unshielded. Every single mechanism of atmospheric loss is running at its highest setting simultaneously. These are the worlds that never get a chance to develop complex chemistry. Before amino acids can form, before oceans can stabilize, before anything interesting can happen in the direction of biology, the air is already gone. The surface is exposed directly to stellar radiation. The temperature swings between day and night are violent. Whatever water existed has either frozen solid or boiled off into space as hydrogen and oxygen, stripped away separately by the same processes that took the rest of the atmosphere. The planet becomes a bare rock, indistinguishable in most respects from an asteroid that somehow ended up in the right orbital zone around its star. The processes themselves are gradual. The outcome, accumulated over enough time, is total. Over billions of years, that slow, quiet bleeding is just as lethal as any catastrophe. As of 2026, we've confirmed the existence of roughly 6,300 planets orbiting other stars. That number sounds large until you remember that astronomers estimate there are at least 100 billion planets in the Milky Way alone. What we've confirmed is a fraction so small it barely registers. It's like taking a single handful of sand from a beach and calling it a survey. Still, that handful tells us something. Those 6,300 planets are spread across about 4,700 planetary systems. And when you look at what kinds of worlds they are, a pattern emerges fast. The catalog is dominated by hot Jupiters, massive gas giants orbiting so close to their stars that a year lasts only a few days. Some of them have surface temperatures above 4,000 degrees Fahrenheit. They're not candidates for life. They never were. After hot Jupiters, the next most common entries are super-Earths and mini-Neptunes. Super-Earths are rocky worlds larger than our own, sometimes 2 or 3 times Earth's mass. Mini-Neptunes sit at the boundary between rocky and gaseous, wrapped in thick envelopes of hydrogen and helium. Both types show up constantly in the data. Earth-sized, rocky, temperate worlds show up almost not at all. That's not because they don't exist. It's because of how we find planets. The two methods we rely on most, the transit method and the radial velocity method, are both biased toward the same kinds of worlds. The transit method detects planets by watching for a star to dim slightly as a planet crosses in front of it. Larger planets block more light and are easier to see. Planets in tight orbits cross in front of their stars more often, giving us more chances to catch them. The radial velocity method measures the gravitational tug a planet exerts on its star, causing the star to wobble. More massive planets produce bigger wobbles. Planets in close orbits pull more frequently. Both methods systematically favor large, close, massive worlds. They systematically miss small, distant, lightweight ones. They miss worlds like Earth. This is a crucial thing to understand about the current catalog. It doesn't represent what's out there. It represents what we can currently see. The instruments we've built are precise enough to find Jupiter-sized objects in short orbits and sensitive enough to find some rocky planets around small stars. But the rocky Earth-sized world at Earth's distance from a sun-like star is still mostly invisible to us. When Kepler and TESS and the other surveys report their numbers, they're seeing the brightest letters in a book and missing most of the text. So how many potentially Earth-like planets have we actually confirmed? The honest answer is not many. Estimates vary depending on how you define the criteria. If you require rocky composition, a mass in the right range, and an orbit within the classical habitable zone of a stable star, the confirmed count sits in the dozens, somewhere between 40 and 80 candidates, depending on how strictly you apply each filter. Out of 6,300 confirmed worlds, that's roughly 1%. And even that 1% is questionable. Several of those candidates orbit red dwarfs, where the habitable zone problems we've already covered apply in full force. Others have estimated masses suggesting they might be more Neptune-like than Earth-like. The truly Earth-analogous planets in the catalog are probably countable on 2 hands. Now think about what the remaining 99% looks like. Hot Jupiters baking in orbits tighter than Mercury's. Super-Earths with surface gravities that would crush the chemistry of biology. Mini-Neptunes with crushing atmospheric pressures and no solid surface to speak of. Rocky planets in orbits so close to their stars that temperatures exceed the melting point of rock. These are dead worlds. Not hypothetically dead, functionally certainly. Absolutely dead in any sense that matters for life. No liquid water, no stable chemistry. No surface conditions that any known organism could tolerate. What the catalog gives us then is not a census of the galaxy, it's a distorted picture skewed toward the most extreme and least life-friendly worlds, simply because those are the ones our instruments can reach. The universe hasn't handed us a representative sample, it's handed us a sample dominated by the most hostile environments that happen to produce the most detectable signals. And even within that distorted picture, the ratio is damning. The worlds that could conceivably harbor life are outnumbered by worlds that obviously cannot, by a factor of at least 50 to 1 in the confirmed catalog, probably more. When you adjust for the observational bias and try to correct for the Earth-like planets we're missing, the total planet population skews towards smaller, cooler worlds, which sounds encouraging until you remember that smaller worlds cool faster, lose their magnetic fields sooner, and are stripped bare more efficiently. The corrected picture isn't more hopeful, it's just differently arranged. We are 6,300 confirmed planets into what will eventually be a catalog of hundreds of billions. The early data is the most dramatic data we'll ever have, the clearest possible signal from the detection methods biased toward finding exactly the conditions that make worlds dead. Even within that small, biased sample, the dead worlds already outnumber the promising ones by a ratio that should give anyone pause. Not every dead world orbits a star. Everything we've discussed so far assumes a sun, a central source of heat and light, something to orbit, something to define a habitable zone. But there's an entire population of worlds out there that have none of that. They drift through the darkness between stars, unbound to anything, moving through interstellar space at speeds too slow to escape the galaxy, but too independent to call any star home. These are rogue planets, and they may be among the most numerous worlds in the Milky Way. There are two main ways a rogue planet gets there. The first is ejection. In the early life of a planetary system, things are violent. Giant planets are migrating inward and outward as they interact gravitationally with the gas disk they formed in. Smaller rocky planets get caught in those gravitational interactions. Some get pulled into tighter orbits. Others get flung outward at high velocity, past the outer edge of the system, and out into interstellar space entirely. The early solar system almost certainly ejected planets this way. Most solar systems probably did. The second pathway is direct formation. A cloud of gas and dust can collapse under its own gravity and fragment into clumps. Most clumps massive enough will ignite as stars, but some clumps are too small. They collapse, they heat up, and then they just stop short of fusion. The result is a cold, dark body, wandering space alone, never having orbited anything. The numbers here are hard to pin down, but the estimates are staggering. Current models suggest the Milky Way may contain anywhere from billions to trillions of rogue planets. Trillions. That range is enormous, and it reflects how difficult these objects are to detect. A rogue planet emits no visible light of its own. It reflects no starlight because there's no nearby star to reflect. It's essentially invisible against the backdrop of space. The only technique that can find them reliably is gravitational microlensing, where a rogue planet passes in front of a distant star and briefly bends and amplifies that star's light. The signal lasts hours to days, and then it's gone. You can't go back and look at it again. What are these worlds actually like? Cold, dark. The surface temperature of a rogue planet drifting through interstellar space is somewhere around -200 degrees Celsius, or colder, depending on how much internal heat it still generates and how long it's been alone. There is no day and night cycle. There is no sunlight driving weather, no photosynthesis, no liquid surface water. The atmosphere, if one exists at all, is likely frozen solid, collapsed onto the surface as ice. Cosmic rays, which a magnetic field and stellar magnetosphere would normally help deflect, hit the surface more directly. These are worlds where the basic physical conditions for life as we understand it are simply absent, not degraded. Absent. They represent perhaps the most thorough form of a dead world. The planets we've discussed before at least have stars. They failed to sustain life for specific reasons. Too much radiation, too little atmosphere, too much internal heat, too little magnetic protection. Rogue planets don't get far enough into that story to fail at those specific steps. They're dead at the level of basic energy budget. Life requires energy flow. A living system takes in energy from somewhere, converts it, and uses that conversion to maintain order against entropy. On a rogue planet with no star, no obvious internal heat source, the flow stops before it begins. There is an exception worth mentioning because science tends to have exceptions. Some researchers have proposed that rogue planets with unusually thick hydrogen atmospheres might retain enough internal heat from the radioactive decay of elements like uranium and thorium to keep liquid water stable beneath the surface. The hydrogen atmosphere would act as an insulating blanket, trapping whatever geothermal heat leaks upward from the interior. In theory, a world like that could maintain a warm, liquid layer deep below a frozen crust for billions of years. It's a real idea built on real physics. But it's speculative. The conditions required are specific, and we have no confirmed examples. The vast majority of rogue planets, by any realistic assessment, are dead in every meaningful sense of the word. The Nancy Grace Roman Space Telescope is expected to change our understanding of how many of these objects exist. When it begins its wide-field survey of the galaxy, its sensitivity to gravitational microlensing events should give astronomers the first real statistical sample of rogue planet populations. Right now, the estimates span orders of magnitude. Roman should narrow that range considerably. It won't tell us what these worlds are made of or whether any of them have hydrogen atmospheres thick enough to support liquid water beneath the surface. But it will tell us how many there are, and that number matters. Because every rogue planet is a world that contributes to the total count. We've been building toward a number across this entire video, a rough estimate of how many dead worlds the universe contains. Rogue planets are part of that count, and depending on how many there are, they might represent a substantial fraction of it. Billions is already an enormous contribution. Trillions would change the estimate dramatically. Whatever number the Roman Space Telescope eventually gives us, every single one of those rogue worlds is almost certainly dead. Surface conditions tell only part of the story. We've spent a lot of time looking at worlds that are dead from the outside in, planets that lost their atmospheres, their magnetic fields, their liquid water. But there's another category that complicates the picture. Worlds that look completely dead from space, frozen and dark and airless, but might be doing something interesting far below the surface. To understand what that means, you don't have to look farther than our own solar system. Europa is one of Jupiter's moons. Its surface is a shell of ice, cracked and refrozen, scored with lines where the crust has shifted and refrozen over millions of years. There's no liquid water visible on the surface. From orbit, it looks like a frozen billiard ball. But beneath that ice shell, scientists are now highly confident there's a liquid water ocean, possibly deeper than any ocean on Earth. The heat keeping it liquid doesn't come from the sun. Europa is far too distant for that. It comes from Jupiter's gravity, which squeezes and flexes Europa's interior as it orbits, generating heat through friction. That process is called tidal heating. Enceladus, one of Saturn's moons, does the same thing. Actually vents water vapor from cracks near its south pole, a subsurface ocean actively leaking into space. Us, a direct sample of what's down there. Now scale that up. If moons in our own solar system can maintain liquid water oceans through tidal heating alone, then exoplanets in cold orbits, worlds well beyond what we'd normally call the habitable zone, might be doing the same thing. A rocky planet orbiting far from its star, in a multi-planet system with strong gravitational interactions, could be flexed and heated from within. From the outside, it would look dead. Frozen surface, no atmosphere worth measuring, no signs of chemistry we'd normally associate with habitability. But deep below the ice, liquid water could be circulating. Minerals from the rocky seafloor could be dissolving into that water. Chemical gradients could be forming. These are the basic ingredients that, in the deep ocean vents of Earth, support entire ecosystems with no sunlight whatsoever. This matters for how we count dead worlds. If we define a dead world strictly as a world with no surface habitability, then these frozen ocean worlds probably qualify. Their surfaces are dead. But if we define dead as a world with no environment anywhere capable of supporting life, the answer becomes much less clear, and that distinction shifts the numbers we're building toward. Most fail to grasp what follows. The conditions required for a subsurface ocean to be habitable are surprisingly specific. The tidal heating has to fall within a narrow range. Too little, and the ocean freezes solid all the way down. Too much, and the world becomes geologically violent. Oceans boiled away from the inside. A volcanic catastrophe with no stable liquid environment surviving long enough for chemistry to organize itself into anything. Europa sits in a fortunate zone. Most tidally heated worlds probably don't. The chemistry also has to cooperate. A liquid water ocean sitting in contact with the right kinds of rock can produce the chemical energy gradients that life needs. But not every rocky seafloor delivers the right minerals. Not every ocean has the right pH, the right salinity, the right concentration of dissolved compounds. And there's another problem. For life, as we understand it, to persist and diversify, it probably needs exchange between the deep ocean and the surface, between different chemical environments, between layers. On Earth, that exchange happens through plate tectonics, ocean circulation, volcanic venting. In a sealed subsurface ocean under kilometers of ice, exchange may be limited or effectively absent. The ice shell is both protector and prison. Rogue planets add another layer to this. Some researchers have proposed that rogue planets with thick hydrogen-rich atmospheres could insulate their surfaces enough, combined with heat from radioactive decay in the core, to maintain subsurface liquid water. No star required, no tidal flexing required, just residual internal heat and a thick enough blanket of atmosphere holding it in. These worlds would be cold and dark and completely isolated from any stellar energy source, drifting through interstellar space. But somewhere deep inside, liquid water might persist for billions of years. It's speculative. We have no confirmed examples. We don't yet have instruments capable of detecting subsurface oceans on planets in other solar systems, let alone on rogue planets drifting in between them. What we do know is this: the more conditions you require to line up, the rarer the outcome. Tidal heating in the right range, the right internal chemistry, an ice shell permeable enough to allow some exchange, a stable orbit maintained over geological time scales. Each of these filters reduces the number of worlds that qualify. The same logic that thins the herd for surface habitable planets operates here too, just with a different set of requirements. Most subsurface ocean worlds are probably dead too, but the honest answer is that we don't actually know. That uncertainty changes the estimate we're building toward. To actually estimate the number of dead worlds in the universe, you have to build a chain of probabilities, and the chain gets uncomfortable very quickly. Most people have heard of the Drake equation. Frank Drake developed it in 1961 as a way to estimate how many communicating civilizations might exist in our galaxy. You start with the rate of star formation, multiply by the fraction of stars with planets, multiply by the fraction of those planets that are habitable, and keep multiplying by smaller and smaller fractions until you arrive at a number. It was always meant to organize our ignorance more than answer a question. But the same structure applies here. Instead of asking how many civilizations exist, ask how many worlds are dead. The math works in the same direction. It just ends somewhere different. Start with the number of planets in the Milky Way alone. Conservative estimates put that figure at around 100 billion. Some researchers think it's higher, closer to 1 trillion when you account for rogue planets and worlds in wide or unusual orbits. But take the conservative number: 100 billion planets in one galaxy. Of those, somewhere between 20 and 50% are thought to orbit within the habitable zone of their star. That's the region where liquid water could theoretically exist on the surface. Apply the lower estimate, and you get 20 billion potentially interesting worlds. Apply the higher estimate, you get 50 billion. That sounds promising. That's the last step where the numbers feel encouraging. Now apply the first filter. How many of those habitable zone worlds are actually rocky? Gas giants and ice giants can sit in habitable zones too. They don't have solid surfaces where liquid water pools. They don't have the chemistry that drives biology as we understand it. Estimates vary, but rocky planets may represent a fraction of all habitable zone worlds. Knock the number down. Apply the second filter. How many of those rocky habitable zone planets have retained a meaningful atmosphere? We've spent the last several sections walking through how many ways a planet can lose its air. Low gravity accelerates atmospheric loss. No magnetic field accelerates it further. Close orbits around active stars accelerate it more. Many small rocky planets formed in habitable zones have been stripped bare over billions of years. Knock the number down again. Third filter: magnetic fields. Earth's magnetic field exists because our iron-nickel outer core is still liquid and convecting. Smaller rocky planets cool faster. They lose their dynamos sooner. A planet that loses its magnetic field early loses its atmospheric protection at the same time. Most rocky planets smaller than Earth have probably already crossed that threshold. The Milky Way is roughly 13 billion years old. Many of its rocky planets formed early. They've had billions of years to cool, collapse, and go dark. Knock the number down. Fourth filter: stellar activity. 7 out of 10 stars in the galaxy are red dwarfs. Habitable zone planets around red dwarfs orbit close enough that stellar flares hit them with enormous intensity. Research has shown that far ultraviolet radiation from red dwarf flares is on average 3 times more energetic than previously assumed. Superflares from young red dwarfs can strip oxygen and nitrogen directly from a planet's upper atmosphere. A model suggests a young red dwarf could render a close-in planet uninhabitable within tens to 100 million years. That's a brief window. Most planets around most stars never get past it. Knock the number down. Fifth filter: tidal locking. Planets in red dwarf habitable zones orbit so close that they almost certainly become tidally locked. One face permanently toward the star, one permanently away. The extreme temperature differentials this creates may prevent stable surface conditions. A narrow twilight band at the terminator may remain temperate, but most of the planet is either roasting or frozen. The fraction of tidally locked worlds that develop and sustain life is likely very small. Knock the number down. By this point, you've started with tens of billions of candidates and applied 5 consecutive filters, each removing a substantial fraction. The number still standing at the end is a small fraction of what you began with. And this is before you ask harder questions. whether the chemistry happened to produce self-replicating molecules, whether those molecules survived long enough to form cells, whether cells survived long enough to become something complex. Those filters are even less forgiving. They're the ones we understand least. But for our purposes here, even stopping at the planetary survival filters gives you a stark picture. If only 1 in 1,000 habitable zone rocky planets actually manages to sustain surface life, then 999 out of every 1,000 are dead. If the true fraction is 1 in a million, which some researchers consider more realistic given everything we've discussed, then the ratio tips further. For every living world, there are 1,000,000 dead ones. Not 1,000, 1,000,000. Now take that ratio and move it outside our galaxy. The observable universe contains an estimated 2 trillion galaxies. Each of these galaxies contains on the order of hundreds of billions of stars. The total planet count across the observable universe is somewhere in the range of a septillion. That's a 1 followed by 24 zeros. Apply even the most generous survivability fraction and the number of dead worlds remaining is measured in quintillions at minimum. A quintillion is a 1 followed by 18 zeros. Numbers at that scale don't mean much to us as humans. We didn't evolve to hold them. But they are real. The math is real. The filters are real. Run those numbers across 2 trillion galaxies and you arrive at a figure so large it becomes meaningless, except as a reminder of how exceptional a living world must be. The universe is 13.8 billion years old, vast beyond comprehension, and as far as we can tell, completely silent. That silence has a name. The physicist Enrico Fermi asked the question first, and it's been haunting astronomers ever since. If the universe is this old and this large and planets are this common, where is everyone? Where are the signals? Where are the transmissions? Where is any sign at all that something else out there figured out what we figured out? The math seems to demand that we shouldn't be alone, and yet we listen, and we hear nothing. There are a lot of proposed answers. Some say civilizations destroy themselves before they can broadcast. Some say they go quiet deliberately. Some say the distances are simply too vast for any signal to reach us in a meaningful time frame. Those answers might all be partly right, but everything we've covered about dead worlds points toward a different answer, and it's one that doesn't require catastrophe or silence or cosmic distances. It just requires that the gauntlet is harder than it looks. Think about what a planet has to survive to get from raw rock and gas to a world with living things on it. It needs to hold an atmosphere against constant bombardment from its star. It needs a magnetic field strong enough to deflect the solar wind, generated by a core that has to stay liquid for billions of years. It needs to sit in the right orbital band, not so close that water boils off, not so far that it freezes permanently. It needs to avoid the kind of giant impact that could strip its atmosphere in a single event. It needs a stable axial tilt so seasons don't swing into extremes that wipe the surface clean every few thousand years. And it needs all of this not just for 1,000,000 years or 100 million years, but for long enough that chemistry can organize itself into something that replicates, evolves, and eventually looks up. Each one of those requirements cuts the candidate list down, not to zero, but substantially. And the cuts compound. A planet that survives stellar flares but loses its magnetic field early still ends up dead. A planet with a great magnetic field that sits just inside the inner edge of the habitable zone still ends up dead. The filters don't care that a world almost made it. Almost doesn't count. This is what the rare Earth hypothesis actually argues at its core. It's not that life is chemically impossible elsewhere. It's that the specific combination of conditions required to keep a world alive long enough for life to arise and persist is statistically uncommon. Each condition is individually plausible. We can imagine worlds with magnetic fields. We can imagine worlds in the habitable zone. We can imagine worlds that survived early bombardment. But the overlap, all of those things being true at once on the same world for billions of uninterrupted years, that overlap may be genuinely small. The dead worlds we've spent all this time describing are the evidence. Stripped atmospheres around red dwarf planets, runaway greenhouses on Venus-type worlds inside the inner edge, frozen magnetically dead rocks like Mars, tidal Venuses baked from the inside, rogue planets drifting through interstellar space with no energy source at all. These aren't edge cases. They appear to be the norm. What's rare is a world that dodged all of them. Here's what that means for the silence. If the great filter, the barrier that keeps intelligent life from becoming common, sits mostly behind us rather than ahead of us, then most of the civilizations that never contacted us didn't go quiet. They never started. Their worlds died first. The planet that might have produced them was stripped of its atmosphere 3 billion years ago by solar wind, or it locked tidally to a red dwarf and its night side froze while its day side baked, or its core cooled fast and its magnetic field collapsed before the chemistry had time to do anything interesting. The silence isn't a mystery in that case. It's an answer. It's what a universe full of dead worlds sounds like. None of this means we're definitively alone. The universe is large enough that even a 1 in a trillion outcome happens trillions of times. There could be living worlds out there. The distances might just be too vast, the signals too faint, the timing too misaligned for us to have caught anything yet. The silence doesn't prove absence, but it is consistent with scarcity. And scarcity is consistent with everything the dead world count implies. We passed the gauntlet. Something about the combination of factors that describe Earth, the size, the orbit, the star, the moon, the field, the plate tectonics, the age, came together in a way that kept the chemistry running long enough for all of this to happen. Most worlds, by a very wide margin, didn't get that outcome. They went through the gauntlet and came out the other side as bare rock or frozen desert or dense atmospheric hell. A universe mostly full of dead worlds is one explanation for why, despite all the time and all the space, we haven't heard a word from anyone. The saddest dead worlds are the ones that almost weren't. Mars is the clearest example we have. Around 4 billion years ago, Mars looked genuinely promising. It had rivers, it had lakes. Most scientists now believe it had at least one substantial ocean covering a large portion of its northern hemisphere. The surface was warm enough for liquid water to persist, not just briefly, but possibly for hundreds of millions of years. That's a long time. Long enough, some researchers argue, for primitive microbial life to have emerged. Life on Earth appeared within a few 100 million years of the planet cooling enough to support it. Mars had a similar window. The chemistry was there. The water was there. The energy sources were there. Then the window closed. The core cooled. The magnetic field weakened and eventually collapsed. The solar wind had direct access to the atmosphere and began stripping it away. The pressure dropped. The temperature dropped. The liquid water froze or evaporated into a sky too thin to hold it. Whatever chemistry had been building on the Martian surface, whatever reactions had been running in those ancient rivers and shallow seas, simply stopped. If anything alive had managed to get started, it died when the atmosphere left. Not quickly by human standards, but geologically fast. The conditions that took hundreds of millions of years to build collapsed in a fraction of that time. That's what makes Mars so striking as a case study. It didn't fail from the start, it had its shot. Venus is the same story told at higher temperature. Early Venus may have had liquid oceans. The young sun was roughly 30% dimmer than it is today, which meant Venus received less heat than it does now. Models suggest Venus could have maintained liquid surface water for up to 2 billion years before the sun brightened enough to push it over the edge. 2 billion years. Earth is 4.6 billion years old, and complex multicellular life only emerged around 600 million years ago. Simple microbial life appeared much earlier. 2 billion years of stable surface water on Venus would have been more than enough time for something to start. Whether it did or not, we have no way of knowing. By the time we could look, Venus was already unrecognizable. 880 degrees Fahrenheit at the surface. Atmospheric sea pressure 92 times Earth's. Whatever history Venus had before the runaway greenhouse took hold is buried under a planet that has essentially erased itself. These aren't isolated cases in our solar system. They're almost certainly representative of what happened on billions of worlds across the galaxy. Think about what the habitable zone actually means. It's not a guarantee. It's a region around a star where liquid surface water is theoretically possible under the right conditions. A planet can sit inside that zone and still be dead. What matters isn't just location, it's duration. How long has the planet been in that zone? How stable has its climate been? Has it had enough time for chemistry to assemble itself into something replicating? A world that's been in the habitable zone for 4 billion years has had a fundamentally different opportunity than one that's been there for 100 million years. The second world might check every box we look for: rocky surface, right distance from its star, probably water present, and still never develop life simply because the clock ran out too soon. The window opened. Nothing got through. The window closed. Stars change their luminosity over time. Planetary orbits shift over long timescales due to gravitational interactions with other planets in the same system. Magnetic fields decay as cores cool. Atmospheric pressure changes as gases escape or get locked into the surface. Any one of these processes can interrupt a habitable period. A world that was in the zone 3 billion years ago might sit outside it now. A world in the zone today might have been frozen solid during the exact period when its chemistry was most capable of assembling the building blocks of life. The concept astronomers call habitable duration captures this. It's not enough to be in the right place. You have to be in the right place for long enough, and that turns out to be a surprisingly demanding requirement. Most rocky planets that have ever sat in a habitable zone probably didn't stay there, or didn't stay stable enough, or didn't survive long enough in the right conditions for life to emerge and take hold. The ones that did are almost certainly a small fraction of the total. The rest ran the experiment and got no result. The chemistry churned. The water sat there. The energy flowed through the system. And then something changed. The magnetic field, the atmosphere, the orbit, the star, and the conditions dissolved before the process could complete. Those worlds are dead now, not because they were always hostile, because they were almost right for almost long enough, and then they weren't. The window for life to emerge may be long by human standards, but it's brief by geological ones, and most worlds that opened that window closed it again before anything could climb through. The most common types of planets we've found are nothing like Earth, and that fact alone tells us something important. When astronomers survey the exoplanet catalog, 2 types of planets show up again and again. Super-Earths, rocky worlds larger than Earth but smaller than Neptune, typically somewhere between 1.5 to 2 times Earth's radius. And mini-Neptunes, worlds wrapped in thick gaseous envelopes sitting at the boundary between rocky and gas-dominated planets. Together, these two categories make up the majority of everything we've confirmed. Earth-sized rocky planets in stable, moderate orbits are actually the exception. They're the minority. The universe, or at least the part of it we can see, seems to prefer building something other than Earth. That matters for our dead world count in a significant way. Take super-Earths first. On paper, they look promising. More mass means stronger gravity, which helps a planet hold on to its atmosphere instead of losing it layer by layer to the solar wind. More mass also means more internal heat, which means a longer-lasting molten core, which means a magnetic field that sticks around for a longer time. Those are real advantages. A super-Earth is, in some ways, a more durable version of a rocky planet. But most of the super-Earths we've actually found aren't sitting in quiet, moderate orbits. They're close, very close to their stars. Some complete a full orbit in just a few days. At those distances, surface temperatures can reach thousands of degrees. The atmospheres on these worlds, if they ever had them, have been scorched away or are made of vaporized rock and metal. These are sometimes called hot super-Earths, and they are dead in the most absolute sense. Not stripped bare like Mars, not cooked slowly like Venus. Fundamentally, structurally incompatible with any chemistry that leads to life. The super-Earths in actual habitable zones are far rarer in the catalog, and they face a familiar set of problems. Stellar activity, tidal locking, the question of what their atmospheres are actually made of. A super-Earth in the habitable zone of a red dwarf is still orbiting close enough that flares hit it hard. Its larger mass may have helped it hold an atmosphere, but that same proximity to an active star means the atmosphere it retained might be stripped of hydrogen, oxygen, and water over time. Bigger isn't always better. A larger planet surviving longer against atmospheric loss is only an advantage if the star it's orbiting gives it time to matter. Mini-Neptunes are a different problem entirely. These worlds have thick envelopes of hydrogen and helium wrapped around rocky cores. The pressure at depth inside a mini-Neptune is extraordinary, far beyond anything on Earth's surface. The chemistry at these depths is interesting in a purely theoretical sense, but nothing about those conditions resembles the environment where life emerged here. No stable liquid surface, no shallow tidal pools, no sediment layers where complex molecules could accumulate and experiment over millions of years. Some researchers have proposed a specific subclass called Hycean worlds. The idea is that certain mini-Neptunes might harbor vast global oceans beneath hydrogen-rich atmospheres, with conditions at the ocean surface warm enough for liquid water and possibly even simple chemistry. It's a genuinely creative hypothesis, but the evidence is thin, and even if Hycean worlds exist, and even if some of them have the right temperatures, the chemistry of a hydrogen-dominated atmosphere is deeply different from what Earth had when life emerged. Whether life as we know it could exist in that environment is not a question anyone can answer confidently right now. And here's what most people don't realize about the mini-Neptune category. There's a gap in the exoplanet size distribution, sometimes called the radius gap or the Fulton gap, where planets between roughly 1.5 and 2 times Earth's radius appear less common. Below that gap are rocky super-Earths. Above it are mini-Neptunes. The gap itself is thought to exist because photoevaporation, the slow stripping of gaseous envelopes by stellar radiation, pushes planets in certain orbits from one category to the other. In other words, many mini-Neptunes may have started as something else and lost their envelopes. Or what we're calling a rocky super-Earth today was a mini-Neptune that got stripped. Either way, stellar radiation is doing enormous work reshaping these planets, and that work rarely produces something more hospitable. It usually produces something more dead. Step back and look at the full picture. The two most common planet types in the confirmed catalog are super-Earths and mini-Neptunes. Most of the super-Earths we've found are in orbits too close for life. The ones in habitable zones face severe atmospheric threats. The mini-Neptunes have surface conditions nothing like Earth, and the most optimistic scenarios for them rest on hypotheses that haven't been confirmed. Neither category looks like a promising host for life. Both categories are everywhere. That's not a coincidence. That's a pattern. The galaxy appears to build these worlds efficiently and in large numbers, and almost none of them end up with the stable, temperate, chemically active surfaces that a living world requires. The most abundant planets in the galaxy are almost certainly not the ones most likely to harbor life, which means the dead worlds outnumber the candidates even more severely than the raw planet count suggests. For a long time, estimating the number of dead worlds was almost entirely theoretical, but that's beginning to change. We've spent the last several decades building models, running simulations, and extrapolating from what we know about Mars and Venus. Those models have been useful, but models are only as good as the assumptions behind them. What scientists have wanted for years is actual data from actual exoplanets. Direct evidence. Something that tells us whether the theoretical picture matches what the universe actually looks like up close. In the last few years, we've started getting that evidence, and what it's showing us is not particularly encouraging for anyone hoping to find a second Earth. The most famous case is TRAPPIST-1. It's a red dwarf about 40 light-years from Earth, which in astronomical terms is practically next door. In 2017, astronomers announced that TRAPPIST-1 had 7 rocky planets. 7. All of them roughly Earth-sized. 3 of them sitting inside the system's habitable zone, at the right distance from the star to theoretically allow liquid water on the surface. The announcement was enormous. The coverage was everywhere. Here was a real system, confirmed, with multiple potentially habitable worlds orbiting a single star. For a few months, TRAPPIST-1 felt like the most exciting address in the galaxy. Then researchers started working through the details. TRAPPIST-1 is an old star, but when it was young, it was far more active than it is now. Young red dwarfs are violent. They produce intense flares. They bathe their surrounding planets in ultraviolet and X-ray radiation at levels that would be catastrophic for any atmosphere not shielded by a strong magnetic field. Models suggested the inner TRAPPIST-1 planets had been exposed to this radiation for hundreds of millions of years during the system's early period. That's long enough to strip an atmosphere entirely. The outer planets were less exposed to the flares, but they orbit farther out, where temperatures may be too low for liquid surface water without a thick greenhouse atmosphere to hold heat in. What looked like an ideal neighborhood started looking like a trap, but models are still models. What changed everything was the James Webb Space Telescope. JWST launched in December 2021. It's the most powerful space telescope ever built, and one of its central science goals is directly characterizing the atmospheres of small, rocky exoplanets. It can't see these worlds as anything more than points of light, but it can analyze the thermal emission coming off their surfaces, and from that, it can determine whether substantial atmospheres exist. An atmosphere retains heat. A bare rock radiates it away quickly. The signature of each is distinct. Astronomers pointed JWST at TRAPPIST-1b first. TRAPPIST-1b is the innermost planet, the one most exposed to the star's radiation. The measurements came back. The planet's dayside temperature was about 230 degrees Celsius. That sounds hot, and it is, but it's actually close to what you'd expect from a bare rock with no atmosphere absorbing and redistributing heat. If there were a thick atmosphere, the temperature would look different. It didn't. The conclusion from the data was stark. TRAPPIST-1b shows no evidence of a substantial atmosphere. Then they looked at TRAPPIST-1c. TRAPPIST-1c is the second planet, slightly farther out, and one of the ones located near the inner edge of the habitable zone. More hope was attached to this one. The results were similar. The dayside temperatures were consistent with a bare or nearly bare surface, not a world wrapped in a thick atmosphere capable of supporting liquid water. Not dead in the same way Mars is dead, not confirmed barren, but the evidence was pointing strongly in that direction. These are 2 data points, 2 planets. The sample is tiny, and scientists are careful about drawing sweeping conclusions from limited observations. The JWST survey of TRAPPIST-1 is ongoing, and the outer planets haven't been fully characterized yet. There's still science left to do here. But the early returns matter, because TRAPPIST-1 was the best case. It was the system specifically held up as the most promising place to look for habitable conditions around a red dwarf. 40 light-years away, 7 rocky planets, 3 in the habitable zone. If any red dwarf system was going to show us something encouraging, this was the one. And what we're seeing so far is stripped surfaces and no air. JWST has also been studying other rocky exoplanets beyond the TRAPPIST-1 system. The results across the broader sample are largely consistent with the same picture: worlds close to their stars, orbiting red dwarfs or other active stars, show little sign of the thick atmospheric signatures you'd expect from worlds capable of supporting life. Some show hints of thin or modified atmospheres. Most show very little. The instruments are sensitive enough to detect carbon dioxide signatures that a Venus-like atmosphere would produce, and in most cases those signatures aren't showing up either. What this tells us is not that life is impossible elsewhere. JWST is working with a small and observationally biased sample. Earth-like planets around Sun-like stars are harder to characterize with current technology, and that survey hasn't been completed. The absence of evidence from a handful of red dwarf planets isn't proof that every rocky world in the galaxy is dead, but it is consistent with everything the theory predicted. The atmospheric stripping that models described for years, the hostile radiation environments around red dwarfs, the vulnerability of small rocky worlds without adequate shielding, all of it is beginning to look correct in the actual data, not just on paper. The James Webb Space Telescope is showing us, one planet at a time, that the universe looks the way the theory predicted: quiet, cold, and overwhelmingly dead. Earth got lucky, and the more we learn about the conditions that make a world alive, the luckier Earth looks. Think about what it actually took. Earth orbits a G-type main sequence star, a relatively calm, relatively stable star that hasn't blasted its inner planets with extreme radiation events every few decades. It sits at just the right distance from that star to keep water liquid on its surface. Not so close that it tipped into a runaway greenhouse cycle. Not so far that its oceans froze solid and stayed that way. That orbital window is narrow. Billions of planets don't land in it. But being in the right orbit isn't enough. Earth is also the right size, large enough that its gravity held on to a substantial atmosphere over billions of years, large enough that its interior stayed hot for a long time, keeping the outer core liquid, keeping the geodynamo running, keeping the magnetic shield active, small enough that it never pulled in enough gas to become a mini Neptune, with crushing pressures at depth and no real surface to speak of. That size range is specific. Most rocky planets we've found are either too small or too large. Then there's the Moon. Earth has one of the largest moons relative to its own size of any rocky planet in the solar system. That moon is not decorative. It stabilizes Earth's axial tilt, holding it within a relatively narrow range over millions of years. Without that stabilization, Earth's axial tilt would wander dramatically, producing extreme climate swings, long ice ages, brutal heating events, cycles that would make sustained life extremely difficult. Mars has no large stabilizing moon. Its axial tilt has varied wildly over its history. That variation didn't help. Plate tectonics is another factor most people don't connect to the question of life and death. Earth's crust is broken into moving plates that grind against each other, subduct, and resurface. This process does something critical. It recycles carbon. Carbon gets pulled out of the atmosphere when it dissolves in rainwater and weathers rock. That carbon eventually gets carried into the crust and subducted into the mantle. Volcanoes then release it back into the atmosphere. This carbon cycle acts as a long-term thermostat, preventing the kind of runaway greenhouse buildup that destroyed Venus. Without plate tectonics, carbon accumulates. The thermostat breaks. And then Jupiter. The largest planet in our solar system sits in an outer orbit and acts as a gravitational shield, deflecting or capturing a large fraction of the comets and asteroids that would otherwise be on trajectories toward the inner solar system. The early solar system was a violent place. Impact rates were orders of magnitude higher than they are today. Jupiter's gravity cleared a lot of that debris, and Earth without Jupiter would have faced a far more intense bombardment, potentially sterilizing the surface repeatedly before life had any chance to establish itself. Every one of these factors, the stable star, the right orbit, the right mass, the large moon, plate tectonics, the outer giant, is individually plausible. None of them is miraculous on its own, but they all have to be present at the same time, in the right configuration, and they all have to remain stable over 4 billion years. That's where the math becomes uncomfortable. Researchers who've tried to calculate the probability of all these conditions occurring together arrive at very small numbers. Some arrive at numbers suggesting Earth-like planets are genuinely rare, perhaps 1 in 1,000 habitable zone planets, perhaps far fewer. Others are more optimistic. But even the optimists acknowledge that the raw count of rocky habitable zone planets significantly overstates the number of worlds that actually support life. This is where the Great Filter concept becomes relevant. The Great Filter is the idea that somewhere along the path from lifeless chemistry to a civilization capable of spreading through the galaxy, there is a step, or several steps, that almost nothing passes through. It filters out the candidates. The uncomfortable version of this idea is that the filter might be ahead of us, waiting in the form of something that ends civilizations before they can expand. The slightly less uncomfortable version is that the filter is behind us. What everything we've covered suggests is that the filter might simply be this: staying alive long enough. A planet has to retain its atmosphere, it has to maintain its magnetic field, it has to avoid runaway greenhouse heating, it has to survive the most violent period of stellar activity from its young star. It has to stay in the habitable zone as that star gradually brightens. It has to avoid being sterilized by impacts. And it has to do all of this while also developing the right chemistry for life to emerge, which itself requires billions of years of stable conditions. Most planets fail somewhere in that sequence. They lose their magnetic field too early. They get stripped by their star. They tip into a greenhouse cycle. They freeze. They get hit. The window closes before anything can climb through it. Earth passed every one of those tests. It passed them over 4 billion years. That's why we're here talking about it. But the passing wasn't guaranteed. It wasn't written in somewhere. It was a combination of factors that came together in a specific way and held together long enough for chemistry to become biology, and biology to become something capable of asking why most other worlds are dead. Every world that didn't have all of those things in combination over billions of uninterrupted years is a dead world. And that description probably fits most of what's out there. So let's actually try to put a number on it. The observable universe contains roughly 2 trillion galaxies. That number alone is hard to sit with. 2 trillion. Not 2 trillion stars, 2 trillion entire galaxies, each one a system of hundreds of billions of stars. If you counted one galaxy per second, it would take you over 60,000 years to reach 2 trillion. Our cognition wasn't shaped by evolution to intuitively grasp quantities of this magnitude, but we need to start there because that's the foundation of the estimate. Each of those galaxies contains conservatively around 100 billion stars. Some galaxies are smaller, some are far larger. 100 billion is a reasonable average. Multiply 2 trillion galaxies by 100 billion stars each, and you get a number with 23 zeros. 10 to the 23rd power. That's the estimated stellar population of the observable universe. And most of those stars, based on what we've found in our own galaxy, have planets. At least one per star on average, possibly more. So the total number of planets in the observable universe is somewhere around 10 to the 24th power. A septillion planets, one followed by 24 zeros. Think about that for a moment. A septillion. Now we start applying filters, and this is where the estimate gets uncomfortable. Knowing how many dead worlds are probably out there changes the way you look at the one you're standing on. Not in a sentimental way. The universe doesn't assign meaning. It doesn't keep score. There's no cosmic ledger where Earth gets credit for being alive while Mars gets marked as a failure. These are just outcomes. Chemistry, physics, gravity, time. Some worlds kept their conditions stable long enough. Most didn't. But we're the ones doing the counting. And that matters. Every atom in every living thing on Earth is participating in a process that hundreds of quintillions of other rocky planets never managed to sustain. The carbon in your body has been cycled through living organisms, through the ocean, through volcanic rock, and back again. That recycling happens because Earth has plate tectonics. Plate tectonics regulates the carbon dioxide in the atmosphere. It prevents the runaway greenhouse that consumed Venus. It's been running for billions of years. Most rocky planets don't have it. Most rocky planets never did. Think about what had to go right. Earth formed at the right distance from a G-type star, stable, long-lived, not prone to the violent flares that characterize red dwarfs. It formed with enough mass to hold an atmosphere, but not so much that it became a gas giant. It ended up with a large moon, probably the result of a collision early in its history, that stabilizes its axial tilt. Without that stability, Earth's seasons would swing wildly over millions of years. Climates would destabilize. Ice ages would come and go on timescales that might not allow complex life to persist. Earth also has a liquid outer core, iron and nickel still molten after 4.5 billion years, still convecting, still generating the magnetic field that deflects the solar wind. Mars lost that field. Mars lost its atmosphere. Mars became what it is now. Earth kept it. So far. The words "so far" are doing a lot of work there. The sun is getting brighter. It's a slow process, about 10% brighter every billion years. But it adds up. In roughly a billion years, the increased solar output will begin to heat Earth's surface, past the point where liquid water remains stable across most of the planet. Photosynthesis will struggle. The carbon cycle will slow. The oceans will start to evaporate. Water vapor will enter the atmosphere, trap more heat, and the same feedback loop that consumed Venus will begin here. Not next year, not in a million years. But on geological timescales, it's not that far away. The magnetic field will also weaken. Earth's core is cooling. It's been cooling since the planet formed, and eventually enough of it will solidify that the dynamo will slow. The field won't switch off suddenly, but it will thin. When it does, the solar wind will have more access to the upper atmosphere. The stripping will begin in earnest. In the very long run, Earth becomes a dead world. That's not a prediction that can be avoided. It's physics. The sun will age, the planet will cool. The same forces that have already claimed hundreds of quintillions of other worlds will claim this one too. But right now, none of that has happened. Right now, the water is liquid. The air is there. The magnetic field is intact. The carbon cycle is running. The sun is in the right part of its life. The moon is in the right place. Every one of those conditions is temporary in the long view of cosmic time, and every one of them is currently holding. That combination, all of it working, all of it simultaneously right now, is the thing that makes Earth unusual. Not sacred, not chosen, just statistically rare against a backdrop of worlds that lost the thread. When you look at the number we built, hundreds of quintillions of dead worlds across the observable universe, and then look at where you are, there are two ways to interpret it. The first is that given enough planets and enough time, the improbable becomes inevitable somewhere. The universe is old enough and large enough that even a vanishingly small probability produces results. We may just be one of those results. An outcome that had to happen somewhere and happened here. The second interpretation is that the conditions that produced Earth were so specific, so dependent on factors that could have gone differently at each step, that our existence is genuinely extraordinary. Not miraculous in any supernatural sense, just extremely, precisely improbable. The kind of thing you wouldn't expect to find even if you searched for a very long time. Both interpretations lead to the same place, a living world in a universe almost entirely without them. It doesn't require any additional commentary. The number speaks for itself. Hundreds of quintillions of dead rocks, frozen moons, stripped atmospheres, baked surfaces, and collapsed magnetic fields. And here, one world where the chemistry never stopped. Against a universe that is almost entirely dead, the fact that this one world stayed alive long enough for something to notice is either a miracle of probability or the most remarkable accident in 13.8 billion years. And honestly, it might be both.